topic. I'm going to introduce to you a method today. I'll just write the title down. It won't mean anything to you until we get to it. But it's this idea of what's called Huckel molecular orbital theory. You might know this name. You might not. This is an actual person. He was kind of in the same ballpark as the other guys like Huckel and some of the other early organic chemists who really started to understand molecular structure kind of not in a quantitative way, but in the early 19th century, late 19th century, early 20th century, finally understood something realistic about chemistry. So Huckel will use his analysis to talk eventually about aromaticity, right? The stability of the anomalous stability of benzene, for instance. And so his approach is a really, really powerful and simple way to qualitatively analyze things like this using molecular orbital theory. But we haven't quite gotten to where we want to apply this theory yet. So I want to talk today about the motivation, about where this is really, really powerful, this powerful approximation we can use. And the example I want to start with today, it follows up from our last class, which was methane. And now I want to go one layer deeper in hydrocarbons, if you will. And I want to look at ethylene. All right, and again, just as you don't remember what ethylene is, right, it's the simplest double bonded hydrocarbon, C2H4, ethylene, ethene, whatever you'd like to call it. It's interesting. I think ethene is the correct notation for it, but the common name is ethylene. Why, I don't know. But I want to talk a little bit about the molecular orbitals of this molecule. We won't go into such detail that we did with methane. I'll talk a little bit about the general idea, but I want to focus on a particular aspect of ethylene's bonds, which is this double bond right here. The double bond. All right, so what I'm going to talk about is where this double bond arises in terms of molecular orbitals, and why the double bond plays a major role in understanding the chemistry of any sort of hydrocarbon with double bonds. Double bonds kind of are the big elephant in the room when it comes to structure, and there's a good reason in terms of molecular orbitals why double bonds play such an important role in chemistry. And so I want to talk a little bit about the structure of ethylene from a molecular orbital perspective, but I'm not going to derive all the orbitals today. We did that with methane. And so there's lots of atoms here, so the more atoms you have, the more orbitals you have, so we'll have a long list of things to calculate. So I'm just going to simplify it and then focus in just on the double bond portion. But before we do that, we should talk a little bit about kind of how we construct the orbitals for this molecule. We're going to do it the same way as methane. We're going to use a hybridization approach where we add atomic orbitals together first and then add them to form molecular orbitals. Just like we did with methane. Right, in methane, we added, the way Pauling did it was added 25% S and 75% P character to the carbon atoms, or the carbon atom, to form 4 sp3 hybrid orbitals. All right, we did it a little differently in class, but the approach is just basically the same thing. We're just adding things slightly differently. They're all perfectly valid. And so we're going to have to change things a little bit for ethylene, because the thing about sp3 hybrid orbitals is that their geometry is wrong for ethylene. Ethylene is a planar molecule. Again, let me write that down in case you don't remember. It's planar. Right, so the whole thing can be fit on the board, if you will. It just fills a rectangle. sp3 hybrid orbitals form a tetrahedral geometry, right? Which means that the bond angles, the HCH bond angles, are about 109.5 degrees, and that's not the case at all in ethylene. First of all, it's not tetrahedral, it's two-dimensional, it's a planar molecule, and the bond length here is actually 120 degrees instead. Right, so we can't use sp3 hybrid orbitals instead. And even if we did, it would give us the wrong answer. So what we do instead is, remember that in the p orbitals, one of the three p orbitals is perpendicular to the plane of the other two. Right? So if I were to draw a coordinate system like this, and in fact I'll stick with this coordinate system the whole day, z pointing up, x in this direction, and y out of the plane, then we have two p orbitals in the plane, the x and the y. Right? They form kind of, if you put them together, they form kind of a square in the xy plane. And then we have an extra set of or extra p orbital that is perpendicular to that plane. Right? So the px and the py's kind of sit like this, and the z sits above it. All right, so if we include this adding this orbital right here, the 2pz, introduces a 3D effect. Right? We're now bonding in 3 dimensions instead of in a plane. Right? Now we can bond perpendicular to the molecule. Right? We could bring an H in this way if we had this orbital accessible. And of course, that's not the case in ethylene. Right? So in ethylene, the planar geometry only requires the 2s orbital for carbon and the 2px and the 2py. All right, so we're going to ignore the 2pz. We're going to leave it out. All right, so our new orbital set for ethylene, our carbon atomic orbital set, initially is the 2s, the 2px, and the 2py. And we're going to hybridize these so to 33% S and 66% P. Right, we're just going to combine them equally together, S plus X plus Y. And what we get out of this are what are called sp2 orbitals. Okay, so now the carbon, the orbitals we're using to form our molecular orbitals from carbon are 3 sp2 orbitals and the leftover 2px orbital, 2pz orbital that is perpendicular to the plane. Okay, so each atom, each carbon atom has 3 sp2 bonds that are planar. These are all coplanar. Right, they're all in the same plane, and this is perpendicular. All right, a little perpendicular sign there. Okay, so once you do that, when you add these together, again, we can do the same idea. We can form these coplanar sp2 orbitals and bond them to the hydrogens in the same way that we did methane. Remember, methane, we drew a cube, put the hydrogens at these different edges, and then drew our orbital additions that way. For ethylene, we can put our hydrogens in the corners of a box and then have 2 carbons in the center bisected in where the middle is like this. And we can start to form our orbitals like so. These are our sp2 orbitals. All right, so you form a bunch of bonding and anti-bonding molecular orbitals by combining these 3 sp2 orbitals. 2 of them, one for each atom, goes into bonding to each other, and the other 2 go to the hydrogens. Right? One here, one here, one here, and one here. Okay, so that basically defines the whole bonding system in the plane for ethylene. Right, we've accounted for the 4 carbon-hydrogen bonds and the single bond between the 2 carbons here. Okay, so I'll go ahead and start drawing my molecular orbital diagram for this. It's a little complicated. So here's our carbons. Again, we're not worried about the 1s's orbitals, so we don't care about those in carbon. They're really, really deep, so we can just ignore them. And here's our 2p's. So this is our 2p orbitals for each of the carbons. Right, this is carbon 1 and carbon 2. So there's 2 sets each. And then on the other side, we have 4 hydrogens. So these are our 4 hydrogens. 1s orbitals. Right, I'll fill these up. These each have 2 carbons. And these each have 2 unpaired electrons in them. Again, there's 3 orbitals in here, so these are, maybe I should write it like that instead. Maybe like this instead. Like that. And then I'll go ahead and form these sp2 carbon orbitals. We'll deal with the pz orbitals, the ones that are out of the plane, in a second. So just the sp2 part. And so what happens here? Let's see. Right, so we end up forming a number of really low-lying orbitals that are completely filled. Form the sigma combination from the 2 s's and the hydrogen orbitals adding together. We also form another set. I'll label these 1 and 2 that come from the hydrogens as well. And then from the pi orbitals, you form 3 different bonding orbitals in the plane. And these are all sigma. And so these are the orbitals that you form from the sp2. You get 5 of them. 5 combinations, and then of course you get a bunch of high energy antibonding orbitals as well. Let's see, 1, 2, 3, 4, 5. Like this as well. These are our sigma star orbitals from the sp2 bond. So this is sp2 antibonding. Again, we don't have to worry about this. They're super high energy, and these right here are sp2 bonding. All right, I don't really care about these so much, and the reason why is because when I start to fill electrons, they're all completely filled. How many electrons do I have? I have 4, 6, 10. So 1, 2, 3, 4, 5, 6, 7, 8. I actually have 12, don't I? I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Sorry. So all of these are completely filled, and I'm left with 2 electrons. And I've filled up these. There's 5 that I've filled with the sp2 bonding orbitals. There are 5 orbitals. There are 10 electrons that can go into them. We have 12 total. So there's 2 left over. All right, and those last 2 we have to put somewhere, but we're out of orbitals for a second. Right? We've already, so basically these are the 5. These 5 orbitals are the ones that come from this bond. Right? This sp2 bonding in the plane. All right, but ethylene. So again, I'll draw it like this. This is what we have so far. Our single bonds between the carbons and the hydrogens, like so. Again, we have 5 molecular orbitals. We have 5 bonds, 10 bonding orbitals, each of them. So we have, let's write that down. So the total bond order is 1/2, 10. Sorry, so let me not do that yet. Hold on, let's just hold on to that. But we have 5 bonds, 10 electrons, which means that each bond is a single bond. All right, yeah, so the bond order, now I understand what I did wrong with my math. It's 1/2, 10 minus 0, which is 5, and so per bond it's 1. Right? We get a single bond between all of them from sp2. All right, but we're left with, we have 2 orbitals left over we haven't used yet, which are the p orbitals out of the plane. right? So maybe if I draw it like this instead. Try to make this look as obviously out of the plane as possible. Man, I really can't draw today. So here's my hydrogens. Basically, I'm setting it so these hydrogens are out of the plane and these are in the plane. So we're kind of looking on the edge on. Those are our sp2 bonds. But we're left with two more orbitals, these p orbitals, that we haven't discussed yet, right? They were left out of the hybridization scheme, and now we have to do something with them. Well, it should be pretty obvious what we can do with them. These can overlap with each other if they're the same sign, right? So if I mark them like this, we now have constructive overlap between the orbitals, right? Same sign on both sides. Likewise, there's another combination where they're flipped. I'll just draw it like this. Right? And these combinations, which are pi orbitals, remember these are pi orbitals, they have a node in the middle, we call them pi instead of sigma, is going to be 2pz plus 2pz. And this other one, which is the antibonding orbital, is 2pz minus 2pz. Okay, so there's an extra pair of molecular orbitals that we can form from these two p orbitals, sets of combinations of p orbitals. Right, and so let's go ahead and now I can just draw these right into my molecular orbital diagram. They sit right here, like that. We don't connect them to the hydrogens because the hydrogens don't interact with these orbitals at all. And there's no hydrogen contribution to these orbitals because they're out of the plane. The hydrogens don't contribute here. They cancel out. So these orbitals only form from the interaction of the two p orbitals interacting with each other across the bond. Right? The hydrogens have nothing to do with it. Right? And these are pi orbitals. Like that. And this completes our set of molecular orbitals for ethylene. We have two more electrons to fill in. Again, I have 10 here. There's two more that go in there. Okay. The important thing that that we're going to focus on is that in this molecular orbital diagram, again, it's very complicated. There's lots of different bonds, lots of different MOs. The energy scalings are weird. They clump up in weird different ways. It's hard to predict. But the one thing that we can show, or we can predict from here, is that the pi orbitals form the HOMO and the LUMO, right? The highest occupied and the lowest unoccupied molecular orbitals. And in the case of all hydrocarbons with double bonds, or with unsaturations, the HOMO and the LUMO are generally pi and pi star in this way. Always pi and pi star. So all of this sp2 bonding, all of the hydrogen, carbon-hydrogen bonding, this is all really nice, strong bonds. Of course, they're really strong bonds. But because they're so strong bonding, these molecular orbitals tend to be very low in energy. And the pi orbitals, because they only interact with themselves, they don't interact with the other carbons, they don't have a lot of constructive overlap with all the other atoms in this picture. So this is kind of a weak bond. It's a weak bond, so it doesn't split that much in energy. And so that ends up being that the region where most of the electrons end up being at the highest occupied level is in these pi orbitals. All right, so this is kind of, in some ways, the least bonding MOs, or antibonding MOs. And so they always end up being the HOMO and the LUMO. All right, so when you're doing chemistry or you're interacting your molecule with light, the first absorption, the first excitation that occurs electronically is from the HOMO to the LUMO. This is the lowest energy, this transition is the lowest energy transition. Right? So it's the least amount of energy required to move an electron from one state to another in the molecule. Okay, so that means that in terms of chemistry, if we want to do something electronically to our molecule, maybe we want to break the double bond, we want to do something to it, that the chemistry is going to be largely determined by the lowest energy contributor to that motion, if you will. And that electronic motion is the HOMO to the LUMO transition here, which is all the pi orbitals. Right? So ethylene's chemistry is largely defined by interactions with its pi orbitals. Right? Kicking a hydrogen off of ethylene and replace it with something is really, really hard. It's very difficult. There are entire fields in organic chemistry devoted to taking a hydrogen off of a double bond like this and converting it to something else. We call that CH activation. It's hard to do. But if you want to interact with your ethylene in some way that interacts with this pi system, and I'll show you some examples as we go through this class, so the last couple of lectures about some examples. I have a good lecture on it. The ethylene is quite reactive. Ethylene is more than happy to do something and react with something as long as it interacts with its pi orbitals, because they're the ones that have the highest energy and the least amount of bonding. Right? So that's what they tend to define the chemistry of ethylene. And we have a term for these orbitals. The HOMO and the LUMO are called the frontier orbitals. The reason why they're called the frontier orbitals is because they're kind of if you think about accessing this molecule as if you're exploring it, the entry into the molecule's chemistry is through its frontier orbitals, the things at the front of the wilderness of electrons, and that's these HOMO and LUMO orbitals, right? So any sort of chemical process is largely going to involve the most reactive part of your molecule, which here is the double bonds, right? They're the easiest things to break. The CH bonds are much harder. They're much more strongly bound. Okay, and it turns out that as you go through larger systems, right, we add more double bonds, we go to rings, things like that, what we find is that this HOMO-LUMO, the frontier orbitals, the things that have the lowest energy contribution, the most reactive part of your molecule, are always these pi and pi stars. So what we can do, what Huckel decides to do, is say, look, all of this is great, right? All of this sp2 hybridization is great, but it doesn't really teach us anything qualitative about the molecule, right? The real reactivity and the stability of the molecule is defined by the pi system, right? So what we can do instead is analyze our molecules or our orbitals and just don't worry about all these deep ones, right? We know that they exist, all these bonds exist. And what we do is we just focus our model on modeling these frontier orbitals, the pi orbitals. And what we can do is we can simplify our map significantly and calculate what the pi molecular orbitals look like for any system we want with just some simple matrix map. And that's what I want to talk about today. So let's do it for ethylene. All right, so I want to use Huckel's rules, Huckel's approach to calculating the pi orbitals, which I'll explain how, and I'll use it on ethylene first, okay? So we'll do it on ethylene, which is the simplest case, just one double bond. And then what we'll do is we'll extend the model to more complicated examples as we move through. Right? We'll be able to learn, so this is not a quantitative result, and you'll see that very quickly. It's not a quantitative model, but a qualitative one. It allows us to explain how the pi orbitals of a system with a lot of double bonds arrange themselves energetically, and it tells you a lot about the structure and the reactivity of your molecule. Okay? So again, this is purely qualitative. We can make it quantitative if we want. Absolutely allowed to. So what I'm going to do is this. So Huckel's rules are simple. Let each atom in your system contribute one p orbital. Okay? One p orbital. And they're all going to be coplanar with each other, or parallel to each other. Right? So in the case of, my marker's dying. In the case of unsaturated hydrocarbons, each carbon contributes one 2pz orbital, right, to the molecular orbitals. Right? Now what we're going to do is construct our pi molecular orbitals by taking a linear combination of 2p atomic orbitals, 2pz atomic orbitals. All right, I'm always going to assume that the z-axis is the one perpendicular to the plane of the molecule. All right, so for ethylene, I'm going to redraw my molecule. We'll call this Ca and then Cb. Again, there's hydrogens that we don't really care about here because, again, their bonding is much lower energy. We don't really care about them. And we have these 2pz orbitals here. These are our 2pz's. Right? And so our pi MOs are going to be a combination of the 2pz on A plus the 2pz on B. Okay. And so what we're going to do is solve the Schrodinger equation for this linear combination in the way that we did in our LCAL theory, or linear combination theory. All right, so we're going to use matrices. We have the Schrodinger equation is H psi equals E S psi, right, where H and S are matrices, and psi is a vector where its coefficients, its vector's coefficients are the coefficients on the atomic orbitals, right, C1 and C2. The idea is, the implicit is that our components here are psi A, 2pz A, and psi 2pz B. Right? So we're replacing the wave function with a vector, and Hij, the matrix element Hij, is the integral of, say, psi I, H psi j, and Sij is just the overlap between the two. Like so. Okay, so we've seen this before. What I'm going to do is I'm going to simplify this math quite a bit. All right, so our Hamiltonian matrix for this molecule is going to look like H11, H22, H12, and H21. And our S is going to be S11, S12, S21, and S22. And what I'm going to, so the important thing here is that H11, which is the integral of, say, psi A, the 2pz orbital on atom A. I'll write it more explicitly, 2pz A, H, 2pz B. Or sorry, it's the same one, A, right, which is the energy of the 2pz orbital located at A. But that's equal also to the energy of the 2pz orbital located on atom B. They're equivalent. Right? And so that means this is also equal to H12. Okay, so these are equal, and these are also equal. So H11 is H22 because each atom is equivalent. Right? They're both formed, both atomic orbitals are the same, and H21 is H22 just by symmetry. What would you say? As it's required. I don't know how else to say. H21 is H12, sorry. just by commutivity. Just by algebra, they're equivalent. So what I'm going to do is I'm going to let the diagonal values, h11, h122, I'm going to just call it alpha. All right, just the number alpha. All right, we don't know the actual value of it. We're just going to call it alpha. All right, we're not going to actually calculate it. This is why it's qualitative. All right, so I'm just going to call it alpha. And I'm going to call h12, which is the same as h21, beta. All right, we don't know if what alpha and beta look like. We have no idea. But let's just say their values alpha and beta. Okay, so my Schrodinger equation now. And then I'm also going to make one more assumption that S11, which is equal to S22, is 1, which is by normalization. And S21 is equal to S12, which is equal to 0. And so I'm going to assume they're orthogonal to each other. All right, so my Schrodinger equation now is alpha beta alpha times C1 C2 is equal to the energy times 1 0 0 1 C1 C2. This is equivalent, if I subtract both sides, this is equivalent to writing alpha minus E, beta alpha minus E, C1 C2 is equal to 0. All right, so this is our Schrodinger equation for this simplified problem. Again, alpha is our atomic orbital energy, which is the 2pz, and beta is the resonance integral. It's the so we call this resonance, which is how much does one atom talk to another. All right. Typically, the actual values, alpha is much larger than beta. All right. Much larger. Beta tends to, it depends on the molecule, but we can talk a little more about that, but alpha is usually a big number and beta is a small number. All right, so how do we solve this problem? All right, well, so what I'm going to do is I'm going to show you how to do it in Wolfram alpha. Really easy. So there's lots of different ways to solve this equation. All right, and if you look in the textbook or look online for Huckel molecular orbital theory, there's lots of different ways to solve these problems. But the idea of what Wolfram alpha is going to do for us is, or any sort of method, is going to find a C1 and C2 and a set of energies that satisfies this equation. Okay, so there's going to be a set of C1s and C2s we can pick, and a set of energies that we can pick. There's going to be two solutions because there's two rows. This is two equations, right? So there's two knowns and two unknowns, so there's going to be two solutions. So we're going to be able to use Wolfram alpha to take in this matrix and have it calculate the vectors and the energies that give us 0 when we do this math together, when we multiply all this out. All right, and so these vectors, so I'm going to give you the names for these. If you've taken linear algebra, you might recognize these. The vectors that solve this have a specific name. They're called eigenvectors. And the energies that satisfy this expression, which are the energies of the molecular orbitals, are called the eigenvalues. So what I can do is I can type in a matrix on the Wolfram alpha and have it ask it what are the eigenvectors and the eigenvalues of it, right? And it'll give me the results. Let me show you that. Really easy. Now, there's lots of different ways to do this problem. You can do it with old school algebra. You can do it in MATLAB. You can do it in Wolfram alpha. It doesn't matter, but I like doing it this way in alpha because it actually gives really nice results. It works really well for this problem. What we want to do, in fact, is what we want to provide it is just the Hamiltonian matrix. So let me write it over here. I'll give you the steps. So we're going to first, in Wolfram alpha, so to compute eigenvalues and eigenvectors, first you want to define the matrix that you want to calculate the eigenvectors and the eigenvalues. Input H, which for ethylene is A, B, B, A. All right? And the way that you do this in Wolfram alpha, the notation for matrices, there's a couple different ways to do it. If you go here to math input, there's this little box here that gives you a bunch of vectors and matrices, and it gives you some standard sizes. All right, so we could put a 2 by 2 in if we want, but eventually we're going to get to bigger molecules. We'll want big matrices that this might not give you. And so let me show you how to input this properly into Wolfram. So matrix input starts with a left squiggly bracket and ends with the reverse. And then each row starts with the squiggly bracket and ends with the left facing squiggly bracket, and each row is separated by commas. So let me write down an example of that, and then you'll see the rules. So the matrix A, B, B alpha, in Wolfram alpha, I would write that again with open squiggly brackets, and then the first row, A, B, close brackets, comma, the second row, B, A. Like that. Okay, so just as another example, we'll see this matrix very soon. Something like this. We're going to have some zeros. I'll explain why there are zeros in it in a little bit. This would be A, B, 0. Then in squiggly brackets, B, A, B. Then in squiggly brackets, 0, B, A, squiggly brackets, close the whole thing. All right, so the matrix is a set of squiggly brackets, and each row of the matrix is its own set of squiggly brackets separated by a comma. I think in my notes I have, in my notes I have a note about this. So if you forget it, it's on page something of my Huckel approximation notes, which I have not posted, but I'll post them today after class. So in order to calculate the eigenvalues and the eigenvectors of this matrix, all I have to type in Wolfram alpha is eigenvalues and eigenvectors of, and then I give it the matrix. So our matrix that we want is A, B, B, A. So it looks like this. And you can see it auto-completed for me. I'll do it a little slower. I'm sorry that my speed typing is a little fast. So here's my open bracket. My first row goes in its own set of brackets. When I close the brackets, you'll see it converts it into a vector. And then I add a comma for the next row. And that'll go into curly brackets, close it, forms another vector. And then I close the matrix one to close the whole thing, and it converts it into a matrix automatically. Right? Eventually, you'll get, if you get big matrices like 10 by 10, it might not do this. But this is how you fill them in. Okay? And I'll give you some practice on these as well. Next class, we'll do a bunch of examples. Okay, and so here are the outputs of it. Let me go ahead and erase this. And let me tell you how to interpret these results. So our Hamiltonian for ethylene, for the pi system of ethylene, our Hamiltonian is alpha, beta, beta, alpha. And our eigenvectors, which again are the molecular orbitals, right? So these are the orbitals, the molecular orbitals of the system, are listed as vectors, nu and nu1 and nu2. Right? So there's nu1, which is, what is it, -1, 1, and nu2, 1, 1. And then the energies associated with them, the eigenvalues are lambda. And then energy of 1, which is lambda 1, is alpha minus beta. And the energy of 2, which is lambda 1, lambda 2, is alpha plus beta. Okay, so what that means is quite simple. We are constructing molecular orbitals 2pzb and 2pza, or two carbons. They each have one electron in them. And we're combining them to form new molecular orbitals. The energy of these are at alpha. Right? That's the atomic energy of the system. Alpha, that's the energy they're at. And we form two new molecular orbitals, one at alpha minus beta and one at alpha plus beta. All right? So we have to figure out which one's the higher energy and which one's the lower energy. And the way we can do that is just to look at the eigenvectors. So we have two new molecular orbitals. Our new MOs are 1, 1, and -1, 1. And these are equal to 2pz plus 2pz, 1 times 2pz. Right? The components of these are 2pz orbitals. So this is adding 2pz's together. And this one is 2pz minus 2pz. Right? That's what the -1 says. Right? This vector is 1 times 2pz plus on A plus 1 times 2pz on B. And this one is -1 times 2pz on A plus 1 times 2pz on B. All right, so we can immediately identify these. This is a bonding orbital because it's a constructive addition of 2p orbitals. And this is the antibonding because it's a difference. Right, so we form a pi star and a pi. This is the 1, 1 molecular orbital, and this is the -1, 1 molecular orbital. And their energies are exactly here. This is alpha plus beta, and this is at energy alpha minus beta. Right, so the amount that the molecule is stabilized by when it binds to form the p orbital, the bond strength of the p orbital, the pi bond, if you will, that's an inverse mean, is beta. Right? And the destabilization, the excitation energy, the first excitation in the molecule for the electrons is at 2 beta. So I'll write that down. Bond energy for double bond is beta, and the absorption for pi to pi star, which is the first excitation of the molecule, is at 2 beta. exactly what I wrote down in that molecular orbital diagram for ethylene at the beginning of class. We form a pi combination and an antibonding combination, antibonding combination, from combining two pz orbitals together. All right, and they split evenly by this plus or minus b beta, whatever beta is. Okay, this can be generalized to any problem with double bonds. It can be generalized to lots of different problems, but we'll focus on double bonds in particular. So let me give you another example. I want to compare two different molecules now. Let's use this approach now for a different molecule than ethylene. And again, for ethylene, we get exactly the answer we want. Two new molecular orbitals, a bonding antibonding combination, they're equal and opposite to each other. Exactly like what we would expect. So let's do something a little more complicated. Right, so I want to try this molecule. This is one of my favorites. I want to calculate the molecular orbitals of cyclobutadiene. Okay. Let's use Huckel molecular orbital theory to do this. We'll come up with a new rule that will simplify our math quite a bit here. Right, that we didn't need for ethylene, but we'll need here. I'm going to label these atoms just to keep it simple. 1, 2, 3, and 4. All right, so what we're going to focus in on is the pi system of two pz orbitals on the 4 carbons. All right, again, I assert that these orbitals form the frontier orbitals. Right, they're the ones that are closest to the point at which you no longer have electrons, the HOMO, the LUMO gap. All right, so these are the chemically relevant ones. All right, but now we have 4. Right, so our MOs are going to look like combinations of 4 2pz orbitals on the 4 different atoms. Okay. All right, we're going to combine the individual pz orbitals on each one in the same way that we did for ethylene, but now we have 4. Okay. So we're going to combine 4 atomic orbitals. We would expect to get 4 molecular orbitals out. All right, so let's see if we can. All right, so first what I want to do is construct my Hamiltonian. Right? I don't have to worry about anything else. Right? All I need to do is construct my H matrix, and I know how to calculate the answer in Wolfram alpha. So again, we're going to let the diagonal elements be alpha, and then nearest neighbor. And then what we're going to do is nearest neighbors. So H12, which is equal to H23, which is equal to H34, which is equal to H41, is equal to beta. All right, so we call these nearest neighbors. And then we're going to say, so basically the p orbitals that are next to each other, the neighbors, they talk to each other. And then all the other ones are 0. Okay, so, and again, these are symmetric. So H21 is equal to H32, which is equal to H343, equal to H14, which is beta, right, by symmetry. All the other terms are 0. What that means is that if beta, you talk about the orbitals mixing and talking to each other, they can only mix and talk one atom at a part. So 1 and 2 can talk to each other, 1 and 3 can talk to each other, but 1 and 4 can't. Oh, well, that means this math is wrong here. So, so let me rewrite this. I'm sorry, I just realized I didn't make it. This doesn't make any sense. So we're going to use for beta for the off diagonals. only HI plus or minus 1 is equal to beta. All else are 0. Okay. All right, so let's go ahead and construct this matrix. All right, so only the ones that are next to the diagonals are going to be beta. All right, so we have 4 rows and 4 columns. So we have alpha, 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 and alpha. Those are our diagonals. And then the atoms, remember this is atom 1, or A, B, C, and D. A, B, C, and D. All right, so only the ones that are nearest neighbors are going to talk. All right, so A and B, for instance, is going to have a beta here. Likewise, B and A are also going to have a beta, right? But A and C are not, right? Because they're 2 atoms apart, 2 bonds apart. So that's 0. And then A and D, let me rewrite these again. So this is A, B, this is not the best orientation, sorry. C and D, let's do it like that instead, that's better. So A and B talk to each other, and A and D talk to each other. So this is alpha, right? And we're done there. And then let's look here. B and C talk to each other, but B and D don't. They're on the opposite side, so this is 0. Let's go down to the next one. C and alpha are 2 apart, so that's 0. C and B are 1 apart, so that's beta. And C and D are 1 apart, so that's beta. And then C and D is beta. D and B is 0. And D and A is beta. Okay? So what I've done is I've connected nearest neighbor atoms together, and I've excluded interactions between ones that are 2 apart or further. Of course, the furthest they could be is 2 apart here, but you can imagine in benzene you might have larger molecules, you have more zeros. Okay, so this is what we call the nearest neighbor approximation. Right? That the only way that we can talk is along 1 bond. Okay? This is all we need, right? With this matrix, we can now calculate the eigenvalues and the eigenvectors. So let me rewrite it real quick so I don't lose it on the board. Well, I'll have you read it out to me. How about that? Okay, so now we have a bigger matrix. And again, we want to, each row is going to be its own array. And so what do we have? We have A, B, 0, B for the first row. The next row is going to be B, A, B, 0. The third row is going to be 0, B, A, B. And the fourth row is B, 0, B, A. Is that right? I think that's right. Yes, it is. Okay, so I have this big-ass matrix. Let me close it up with another bracket. So there's my big matrix. Here, and I'm going to calculate the energies and the wave functions for the molecular orbitals from this. All right, not surprisingly, we put in 4 atomic orbitals. We get 4 out. 4 molecular orbitals out. Just like we expect. So let's go ahead and analyze this really quickly. So what we've started with are 4 2pz orbitals. Right, and we're going to combine them together to form 4 new molecular orbitals. And let's write them down. So MO1 is 0 minus 1, 0, 1. MO2, well, let me go ahead and put the energy here. So the energy, again, is the eigenvalue lambda, which is just A, just alpha. MO2 is -1, 0, 1 and 0, is that right? Yeah, 1 and 0. And it also has energy alpha. And then we have two more orbitals at alpha minus plus or minus 2b. So MO number 3 is -1, 1, -1, 1. With energy alpha plus 2 beta, I assume. Minus 2 beta, excuse me. That's right. And then MO number 4 is 1, 1, 1, 1. E4 alpha plus 2 beta. Okay? So what happens here? Well, remember that the energies of these are at alpha. Alpha is the orbital energy that we start with. So we form one that's low energy, alpha plus 2 beta. We form one at high energy, alpha minus 2 beta. And then we form two non-bonding orbitals. Their energies don't change. Like that. Okay, and these are at alpha. All right, so let's look at these molecular orbitals. Just draw them. It's not too hard to draw them. I'll explain how we do that in just a second. To show why these are non-bonding and bonding. All right, so let's look at number 1. This MO is 1, 1, 1, 1. So what I'm going to do is I'm going to draw my square for cyclobutadiene and draw my p orbitals. And the signs of these numbers tell me, or the sign and the magnitude the sign tells me which way they're pointed, right? Whether it's plus or minus pointing that way, the plus phase or negative phase, and the size the number tells me the contribution. So these are all equal contributors, right? They're all 1, 1, 1, 1. So the size of the atomic orbital, the contribution to the MO is all the same here. So these all look the same, and they're all the same sign, which means they're all pointing the same way. Like that. Right? So this is a natural bonding MO because all of the orbitals are connected. Right? They're all overlapped with each other. Right? This is a pi orbital. Pi bonding. Right? So lowest energy, all the orbitals add constructively. Let's look at the high energy one, -1, 1, -1. So again, we have p orbitals on each one. But their sign changes. Right? So -1, 1, -1, 1. Right? So now they're completely destructively overlapped with each other. They alternate signs so they don't overlap at all. Right? So there's a node between these, there's a node between these, a node between these, a node between these. Right? They don't overlap at all. They're completely destructively overlapped. So this is a pi star orbital. Right? Because their sign alternates each atom. All right, we're left with two more. But these have zeros, right? And that means that those atoms don't contribute. So 0 minus 1. So again, if it's 0, there's nothing there. I'll just put a dot. The -1 means it's phased like this. And then we have 0, 1. Okay. And then the other one, it's not too hard to see, it just looks exactly the same, it's just rotated slightly. We have the -1 on the first atom, a 0 on the second atom, a 1 on the third atom, and a 0 on the fourth, right? These are just the same, but just rotated, right? These are equivalent. And they're not bonding. The reason why they're not bonding is because there's no overlap anywhere. These don't talk to each other. They're not nearest neighbors, so they don't talk to each other. Right? Their overlap is 0. And the nearest neighbors to the two orbitals that contribute are 0, so there's no interaction anyway. There's no contribution there. So there's no bonding in general. Right? There's no bonding. Right, bonding in Huckel, I'll just write that note. In Huckel theory is a nearest neighbor only concept. So these two MOs in the middle don't have any nearest neighbor orbitals to contribute, to bond with, or to antibond with. So the only orbitals are across the ring. They don't talk to each other, so there's no net bonding or antibonding. Okay? So these are called non-bonding orbitals. Okay? So let's go ahead and fill our system with electrons. 2 here. And then our HOMO can either be like this or like this. Right? It's either a triplet or a singlet. It's not clear. Okay, so it could be either. Right, so cyclobutadiene in particular is a really interesting molecule, especially when we compare it to its linear version, butadiene, which I don't know if I have time to do today. We might have time to do it. But the important thing to note is that in cyclobutadiene, the HOMO of the system is only half filled. Right? This thing wants to take electrons in. Right? This very what's the opposite? Very low, very high electron affinity. Right? It wants to fill those orbitals up. Right? It has some impetus to fill those orbitals. We don't want half-filled orbitals, obviously. We want to fill like an octet, if you will. Same idea. And so cyclobutadiene was more than happy to accept electrons from anything. Therefore, cyclobutadiene turns out to be extremely unstable. Because the moment it finds anything that's willing to give it an electron, it just falls apart. Very unstable. However, if you put two negative charges, if you reduce it and make it cyclobutadiene dianion 2 minus, is very stable. Not surprisingly, because when you add 2 electrons, it fills the shell, the HOMO shell. Now they're completely full. All right, you can buy salts of this, I think. Pretty sure you can. Cyclobutadiene doesn't exist. Well, it does, but it basically falls apart instantaneously. You can make, in fact, my undergraduate advisor was one of the first people to spectroscopically identify cyclobutadiene, and it followed the rate of its decomposition in the vacuum just from it reacting with itself, not with anything else, just with cyclobutadiene reacting with another cyclobutadiene to fuse together. That reaction, the rate on that occurs, the time scale is on the order of nanoseconds, maybe microseconds. It's very fast. So cyclobutadiene will immediately react with itself to form a stable complex that fills its HOMO up with electrons. Right? It takes some electrons. It basically takes 2 electrons from a cyclobutadiene and kicks off the other 2 to form an ethylene. And I think, in fact, the way that it decomposes is something like this. Like that. Forms a bicyclic compound that's stable. Right, this is fast. There's other ways it can react as well, but this is one of the main ways it reacts. So cyclobutadiene, just by looking at its molecular orbitals qualitatively, you can already predict that it's not a stable molecule because it forms 2 half-filled shell molecular orbitals that are spin unpaired, and so it wants electrons from anywhere. Right? It'll take an electron from anywhere to stabilize. Right? Now, if you remember from organic chemistry, if you remember Huckel's rules, that's where the name comes of. You need 4n plus 2 pi electrons for aromaticity, and 4n electrons is anti-aromatic, which is unstable. This is exactly that. systems that are conjugated that have 4 in electrons, so 4, 8, or 12 electrons, pi electrons, are quite unstable, right? And that entire rule comes from this idea, right? That these systems, when you look at their HOMO, they end up having half-filled shells in their HOMO, and those lead to instabilities, amongst other reasons. All right, we'll look at that more carefully this week or next week. Okay, so what I want to do for like the last 5 minutes is just very, very quickly look at, I want to break this system, break the linear part of the system, or sorry, the cyclic part, and just look at cyclobutadiene instead. Okay. So again, these have the same amount of pi electrons, but they're not connected in a cycle anymore. Right? It's just linear. All right, so I'll label these the same way, A, B, C, D. And let me just quickly write down the matrix for this. It's not too hard to do by inspection. Again, there's no connection here, so A and D don't talk to each other anymore. There's no bond between them. So the H now is going to be alphas on the diagonals, beta for A and B, and then 0, 0. Beta here, then a beta here, and then a 0, right, because C and B talk to each other. And then for C, C talks to B, D, it talks to B, it doesn't talk to A. And then D, I'll write it over here so it's cleaner. D talks to C, and they have zeros everywhere else. All right, so notice these matrices are different. Right, they have the same amount of pi electrons, but because A and D aren't connected to each other, we have a lot more zeros in there than we do here. There's not the cyclic symmetry associated with it. So now you have this kind of weird shape. All right, so when we calculate the eigenvalues of this, I'll just write them down instead of calculating them. The MOs, so the first one, let me see if I have a better number than that. Minus 1 is minus 1. This number is 1/2 plus 1 plus the square root of 5. I'm going to call this, I have to figure out what that number is off the top of my head. 1/2, 1 minus the square root of 5. Notice that the eigenvalues look quite a bit different now, or the eigenvectors. Now they have fractions and radicals in them. And the energy for this is 2 alpha minus root 5 minus 1 beta. And then all the other ones are combinations of these. I won't write them all down. But I'll write down the energies. E2 is 2 alpha minus 5 plus 1, square root of 5 plus 1 beta. E3 is 1/2 2a. Oh, sorry, I miss a factor of 1/2 here. Sorry. So the whole thing is multiplied by 1/2. All of these are multiplied by 1/2. Again, the point that I want to make across here is that the energies are quite a bit different. Quite a bit different than it was for cyclobutadiene. This is minus 1, I apologize. This is minus 1 beta. And this is 2 alpha plus the square root of 5 plus 1 beta. Okay. And so if you put beta to be negative, a small negative number, this is the high energy. These go down in energy. The important thing to note is that these are all different. Right? So in cyclobutadiene, we got 2 non-bonding orbitals that don't contribute at all. They don't have any bonding interaction. Right? They don't change at all. But here, all of the orbitals change energy. Right? So what we get out of this system, so this is the MOs for this system. So our 4 2pz orbitals. we form two pairs of bonding and anti-bonding MOs. Call this 1 pi star, 2 pi, and 2 pi star. And now we can fill them up, right? And now you have all your MOs, your HOMO is completely filled. And bonding. So if I were to draw it, let me get it out. This HOMO looks like this. Let's see, this is number 3. So it's going to be a -1 here. And then 1 minus the square root of 5. This is a small, you got a big one here, like this. Big one here that's opposite, and then a small one here. That. So this system, this HOMO, has two atom bonding interactions and then a nodal plane in between, like that. And the LUMO has two nodal planes and then a bonding interaction in the middle, like this. So it's got two lobes on the outside that don't interact with the center atoms, and they bond. So quite a bit different than cyclobutadiene. Right? Cyclobutadiene, the middle two orbitals, the HOMO is non-bonding. It doesn't know. You just have, effectively, you have electrons isolated on these two atoms. They're not shared across all the bonds in the ring. But here we have sharing between orbitals, and that causes some bonding and anti-bonding effects, right? We have effectively one bond here and one bond here, all separated, and here we just have one bond, right? And the other two are not interacting with it, right? So this is kind of like a 2-bond interaction. This is a 1-bond interaction. Obviously, this is higher energy, because here you have 2 constructive overlaps. But the important thing here is that the HOMO is completely filled, right? So if something comes in and wants to give this system electrons, it has to put electrons into the LUMO, into the unoccupied higher energy orbital, right? If I want to donate electrons from an external source, they have to be high energy. They have to be high energy in order to be pumped into there, and so this system is much less reactive. So butadiene is much less reactive than cyclobutadiene because its HOMO is completely filled. So again, the fact that cyclobutadiene's HOMO is not filled, it has really no impetus to not take electrons here. Right? These are non-bonding orbitals. They can just take an electron. They're effectively like lone pairs or radicals. It's more than happy to take an extra electron from somewhere to add here. Because they're non-bonding, it doesn't destabilize the molecule by adding electrons to it. Doesn't stabilize the molecule either, because they're non-bonding electrons, doesn't increase the bonding, but it does pair the spins, and of course that's stabilizing. You want to fill your orbitals up. But here, the HOMO is completely filled, and the only way that that butadiene will accept new electrons into its system is to put them in the LUMO, which is an antibonding orbital. And that means that this is endothermic. Because in order to put an electron here, you've got to break this bond a little bit. You've got to put some antibonding character in your molecule. And that's not stabilizing, right? It's destabilizing. So putting an electron, adding electrons is endothermic. Right? Adding electrons to butadiene is endothermic. And adding electrons to cyclobutadiene is probably exothermic. The system actually releases energy by adding electrons from an external source to stabilize itself. But adding an electron to butadiene forces you to break those double bonds a little bit by putting an electron in the LUMO, and so that's going to be endothermic, because you have to break the bond a little bit, you have to weaken the molecule. So again, all I've done is qualitative, right? I haven't done anything quantitative here, right? Everything is alpha and beta. But just by doing that, I can already start to do predictions in organic chemistry, right? I can predict that cyclobutadiene is unstable. I can even calculate how much more unstable it is relative to butadiene, which we'll do in class on Monday. And then we'll compare it to benzene as well, the classic example of benzene versus versus hexatriene, the linear version of benzene. All right, and so what we'll show is that butadiene is necessarily lower energy than cyclobutadiene. And then what we'll show with benzene is that it's flipped. Benzene is lower energy than hexatriene. Okay? And this is aromaticity and anti-aromaticity. Okay, so that's it. Your homework 3 has been graded. You should have your grades already. I'll have more information about the take-home final next week. So anyway, we'll get back to Huckel theory on Monday and Wednesday. I've got some examples from organic chemistry to talk about. We'll talk about other applications of this theory. Yeah, and have a nice weekend.
Have a good one, Dr. Seifert.
Yeah, you too. Thank you.